A stick is randomly broken into two pieces. In our experiment, we measure two things. First, the length of the smaller piece, and second, the ratio between the smaller piece and the larger piece. In this video, we're going to find out what happens to these values on average, or what our experiment tends to as we break more and more sticks. Before we start, we need to define a couple of terms. First, the length of the stick. I'm just going to let the length of it be equal to 1 because it doesn't really matter what our length is, as we can scale our answers accordingly later, and I'm going to choose 1 for simplicity. Next, take a look at our very abstract drawing of a stick here, and notice what defines the small and the large piece. They are obviously separated by 1 point, and we can describe this point numerically. I'm going to give it some numerical value t, and this t I'm going to define as the distance from the left end of the stick to the point where the stick breaks. This will make a lot of things very simpler in the future. We need to note some important things about t. First, note that t can only take on the values between 0 and the length of the stick, which we call to be 1. Second, note that t is a random variable. It is something that we are randomly changing. And so we get to assume how t is distributed. And I think by the wording of this question, it's safe to assume that t is uniformly distributed, which means that the probability of choosing t on the entirety of the stick is all the same. Now that we've described t like this, we can define functions of t that measure the lengths of the smaller and larger pieces. Take a look at this. I'll have some function of t, I'll call it x of t, and this will measure the length of the smaller piece. It's going to be a piecewise function for two separate ranges of t. So notice, when t is less than 1/2, so overall on this side of the stick, the smaller piece of the stick is simply going to be this little piece from 0 to t. So simply, x of t is going to be t when t is between 0 and 1/2. Now, when t is greater than 1/2, say we have some point right here, then the smaller piece is no longer going to be all the way up to t. It's going to be 1 minus that, or the length of the stick minus that, which is, in this case, 1. So then we're going to have 1 minus t for t that is in between 1/2 and 1. And this is going to be the length of the smaller piece. Now, the larger piece is much the same, because we can write it as y, for example, it's going to be the larger piece. It's simply equal to 1 minus the smaller piece, because it's simply the whole stick right here. And we can again write it as a piecewise function. It's just going to be the same thing as here, but reversed. So 1 minus t for t between 0 and 1/2, and t for t in between 1/2 and 1. Before we continue, I've left a small footnote here so you don't get confused which is smaller and which is larger. Alright, so moving on, I think it would be very helpful to draw the graphs of these functions x and y. So let's do just that. It's going to look quite simple, as you're about to see. First, for the graph of x, notice t when t is between 1 and 1/2, so just like this. Then it peaks at 1/2 and then goes back down. So this is 1/2, and this is also 1/2. And y is going to look much the same. So t here, y here. Notice 1 minus t when it's between 0 and 1/2, so like this. And then it goes back up like this. And this is again 1/2, and this is also 1/2. Finally, due to our proper setup, our two questions from the beginning become very simple, because now we are just finding the average value of a function on an interval. Doesn't that ring a bell? Let me write down the formula here so you all remember it. The average value for a function on an interval a, b is equal to the integral from a to b of that function over b minus a. Quite simple. I'll put it in the box so we all know. And now we can just apply it to our functions x and y, and it's even more simple because our t is uniformly distributed. In order not to integrate over a piecewise function, notice first that the functions x and y are both symmetric over the lines t equals 1/2. So finding the average of those functions on the interval from 0 to 1 would be equivalent to finding the averages from 0 to 1/2. To answer question 1, we have to find the average value of x on the interval from 0 to 1/2. So that is simply going to equal the integral from 0 to 1/2 of x of t in dt over 1/2. That's just going to be 2 integrals from 0 to 1/2 of t in dt. Notice because the bounds are from 0 and 1/2, therefore x of t is equal to t. So this is simply equal to 2 times, what's the integral of t? It's going to be 1/2 of t squared times 1/2 t squared with the bounds 0 and 1/2. The 0 cancels out, so it's simply equal to 2 times 1/2 times 1/2 squared, 2 times 1/8, which is 1/4. How nice. Now the second question gets a bit more interesting because we have to divide x over y. So really, we're integrating either from 0 to 1/2 of x over y, or 1/2 to 1 x over y. I'm going to choose 1/2 to 1 because that makes the integral a bit easier to do. So this is going to equal the integral from 1/2 to 1 of x of t over y of t, because the ratio dt, and it's again going to be over 1/2. This will equal 2 integrals. So what is x of t when it's between 1/2 and 1? It's equal to 1 minus t. And y of t, that's equal to t. So 1 minus t over t dt with our bounds 1/2 to 1. And we can do this simply. We can write this as twice the integral 1/2 to 1 of 1 over t minus 1 in dt. This is equal to twice of what's this is going to be the natural log, the ln of t, and then minus t, and then with the bounds of 1/2 and 1, and this becomes 2 times minus 1 minus ln of 1/2, and then plus 1/2, which becomes 2 ln of 2 minus 1. And that is going to be our answer to both of these questions. For 1, the average length of the smaller piece is 1/4, and 2, the average ratio between the smaller and larger pieces are 2 ln of 2 minus 1. The reason these integrals were so nice to do is because t was uniformly distributed. Just a quick note here, if t had a general distribution, a general PDF, then to actually compute the averages, we would have to multiply our integrands here by the PDF of t. So yeah, just a quick adjustment. In this case, the PDF was 1, so we were multiplying by 1. And that is it for today's video. Thank you all so much for watching, and I will see you in the next one.